I gave this presentation in the conference of the Operations Research Society in Bangor. I enjoyed it immensely, and I thought I'd make a video of it. It's a combination of a few approaches that come together to facilitate the discussion between a statistical modeler and a subject matter expert. We all do that. It's a very important step, and I thought that adding the causality perspective to that discussion and overlaying it with a little bit of robustness when you explore the data to support that could be very beneficial. And naturally, I have this old work that Yoav Benyamini and I did a long time ago during my PhD, and it kind of felt right to dig it out and look at it again in this context. This is my LinkedIn over here, and this is a link to the paper in archive that is behind this presentation. Now, yeah, and of course, I can't forget mentioning that the images that are presented here, apart from the graphs that are generated by Python, the images themselves are generated using some Gen AI. Usually it's the DALI 3 that comes with the ChatGPT, with the Copilot, and sometimes I use Leonardo.ai. As I was presenting it, I realized that I made a few assumptions, which are definitely correct for the audience that came to that conference, that there's a certain level of knowledge about statistical modeling, about the process of getting into a model that is actually useful, and more importantly, some familiarity with the problem of multiplicity of hypotheses. It's been around for a very long time. If I say the word Tukey, if I say the Bonferroni correction, anybody who's done some introduction to statistics must have heard about them, and specifically the fast discovery rate and the Benjamini-Hochberg. Oh, I got a spelling mistake here. Yeah, the Benjamini-Hochberg procedure to control it, I think is quite ubiquitous nowadays. I'm finding more and more people who know it. I think it's a standard thing to teach nowadays. And in discussions I've had, it was kind of, oh yeah, we just go and use the Python function or the R function that does that. The work that I'm going to mention was originally done with Yoav Benyamini, harking back to the seminal paper that he and Yossi Hochberg wrote in '95. I'm referring heavily to some other papers, including Danny Okotielli's paper. And naturally, this is the technical paper that Yoav and I wrote that I'm going to reuse some of it. So, context. When we generally do analytical statistical modeling, we go for these kind of general steps, and people put some infinity charts on this sometimes, or some recursive, but basically it is you figure out what you want to solve, why you're doing it, what's the aim, what the benefits that you're going to gain from doing the modeling, the analysis. You go into a discovery, talk to subject matter expert, talk to the end users, figure out what they know, what they believe, where do you think the data will be. Then you go and you collect the data, you model it, you report it, publish it, and that's when the subject matter expert sees it again. Nowadays also, by the way, we have here also a step of let's check whether this is compliant with responsible AI and other validations, comparing it to other models. Obviously this process is more sophisticated and advanced, but basically the key issue is that we talk to the subject matter expert here, theoretically, we kind of tell them if we're doing this in Agile or where every demo, we kind of say this is where we are, but we really give it to them to give some feedback and interact with them on the model itself only once we publish it. And I think with a little bit of changing of approach of thinking, we can bring them even closer. This, what I just told you, I've gone through a few mishaps in my life, and one of them was in a company in Austria when we brought these experts from the United States. They did this brainstorming, fishbone chart where we marked out all the potential and logical drivers that could cause churn in that case. Um, and we went and we did a long request with sort of feature engineering. This is how we want the analysis data set, the data mart in the speak parlance in those days. We gave it to the data engineering, and then we sat and we waited and we waited and waited, and we didn't get a response. And the reason that it was delayed was because it was so complicated and hard to do some of those features. Although maybe the data was accessible, they had to order another node. And you don't know really whether all the data that you asked for is relevant, or there are cases where the data, asking for some data, if you don't know how to specify the model correctly, you get something that is complex and misleading. You can go down the route of also discussing whether a complex model is what you want. You can say, I want a model that is most predictive, or you want a model that is most explainable. And you need to know in advance if what you're actually trying to do. What is the business value of explainability? What is the business value of the accuracy of the model? And not always a complex model solves those things. So one of the big problems with misspecifying a model is that you encounter the Simpson paradox. And I just asked the Gen AI to depict something that explains what the Simpson paradox is, and it came up with this. I'm very pleased with it because when you look at it, it looks as if there's these two directions, but really it's a combination of a lot of different effects that are going in other directions. And using causality analysis and having that step of thinking what is driving what and putting it in a directed causality graph is a good way to address or avoid this paradox and avoid also misspecifying the model and identifying which variables are important and not important. So when you do this, first of all, this is a causality graph. Secondly, you show it to people who are not statisticians. They look at it and understand what you're trying to do. They understand the story. Moreover, you do not need one big megalith data set to assess and estimate the relationships between each one of these variables. You can do this one separately, and this one separately, and this one separately, and this one separately. Now, you can handcraft this, and this is what I believe needs to be done, but there is a big body of research out there looking into generating this automatically. So in my code, this is the type of graph I generate. I've got an interpretation for each one of these ways of presentation, but most importantly, I'm saying this is the size of the effect. I'm applying here a linear hierarchical model, SEM, SEM, or sometimes people call it SEM or SCM, so structured equation models or structured causality models. So I've got here the size of the effect, which I estimate, and the p-value around that. Now, I've got here p-values, then I need to ask myself a few questions about that But this is where I want to go. This is the end result. This is the tool for the communication with the subject matter expert. And I go through this process. I'm not going to labor this. The most important thing is that there's a process here with the subject matter expert where the modeler shows the results of the graph. They look at it. They feel whether it makes sense or not, where the p-values say that something is not working correctly, and they try and handcraft it, where the starting point was the beliefs of the subject matter expert. So before we do anything, yeah, we need to ask ourselves, what is the family? Because if you want to do a control of the multiplicity, it is within the context of a family of hypotheses, no matter if you do the family wise error rate or the false discovery error rate. And I'm going to define a few hypotheses now, but there's also the question of, is the family just per step? So I do an iteration, and the hypotheses that belong to that iteration are family, or all the hypotheses that I have directly or indirectly specified in the process of coming up with the model that I use in the end is that family. Now, one of the benefits of using the false discovery rate is that it is consistent also when you take subsets of the family. Not like usually if you take the Bonferroni and you take a subset of hypotheses, you might get different discoveries too if you correct it for the whole family. Of course, this is when the number of true null hypotheses is significantly smaller than the total number of hypotheses. But it's a nice property of the false discovery, controlling the false discovery and the Benjamini-Hochberg procedure. So if I've got a simple directed graph, a treatment, outcome, and a moderator, I will specify it as a simple structured equation model. So the first set of hypotheses are around the coefficients. The second set of hypotheses are about the errors that are normally distributed. And you look at the correlation matrix between these three variables, and you're asking yourself, once I fit this and I look at the correlations that are induced through the model, are they supported with the correlation matrix I observe? The problem with that is that if I just go and do it in the natural, naive way, I will get p-values that are counterintuitive. So all the other p-values for these hypotheses you see on the screen, smaller is good. But if I just compare to the R squares then that are observed, then I'll get the other way around, because I do want them to be equal, right? I do. So I'm going for the biological clinical trials domain, and I define this as an equivalence testing. So as I mentioned, do you need to consider all iterations? I also for my PhD, when I was looking at using the false discovery rate to control the hypotheses that are tested within different statistical process control graphs, several machines on the floor, doing an X-bar chart, a Q-sum, a range chart, all in one go. The conclusion that Yoav and I came to was it makes sense to do it within every iteration. It does not make, there's no benefit to define, and it doesn't change much if you define the hypothesis family as the whole process that you have gone through so far and going to go through in the future. So that's, I'll stick to that. So every iteration is its own family. So I'm going to use here the concept that we came up in our paper, which is the cost-based FDR control, where in this case the cost will be linked to the a priori beliefs of the subject matter expert with regards to the strength of the different relationships there. So if the just for an example, if the subject matter expert will say, I believe that if you drive faster, you will consume more fuel in the car, assign it a weight of 3, and that will translate into a cost. If the subject matter expert says, I'm not sure if a wet road will or will not affect the fuel consumption, then I will assign it to a weight of 2. And if they say, I have no opinion with regards to fuel consumption relationship to holidays or work days, then I'll assign it a weight of 1. Originally, when we did this paper, it was the cost of a fast discovery, where the intention was, because the fast discovery rate is an expectation, building some financial consideration into the rejection and non-rejection. So if a false discovery costs me a lot more than a different fast discovery, I want to kind of convey it to the model, to the process. Just to remind you, if I've got M hypothesis that I test, I observe how many I have rejected. I don't observe, but there is a variable over there, which is how many of the ones that were rejected, the discoveries that I've made, were actually wrong. The fast discovery rate is the expectation of V over R. Family-wise, error rate will be the probability that V is greater than 1. There's nuances to what I've just said. So if I build the cost into it, this is a natural expansion of that. This is a natural expansion of this particular term, where I add the cost of this false discovery to the two terms. And then we added also, and this was quite useful, the cost of the rejecting the whole family of hypotheses, the intersection hypothesis. So if you want to think about it, this will be the fixed cost of making a discovery, and these are the variable costs. So if I get an alert that something is going wrong somewhere on the manufacturing floor, then I need to bring an engineer. Okay, that's this cost over here. Now, depending on what's gone wrong, if it's a machine, a pump, a heating element, or whatever, there's different costs for bringing erroneously an engineer there to try and resolve it. This concept of fixed and variable costs actually creates a nice continuum. By the way, this is the way of possible ways of measuring this particular intersection statistic without doing a different separate hypothesis. You just combine the p-values that you have at the moment in one of these two ways. There's another way also. But this gives me a continuum. So if I have set the values of the costs in certain ways, I get as edge cases the weighted FDR, the FDR itself, or the weak control of the FWE, which is different than the strong control, which everybody knows. To get the strong control, it's not really on this continuum, because it really means that the cost of any erroneous discovery is infinite. So you can create, as an example, I've got here a story around a wind turbine, and I want to make a decision about how fast to let it turn so as to, and the question that I want to know is what will be the noise that will be perceived by the neighbors of this wind turbine farm, and how much energy I'll be generating. So I want to generate some model around that. There's the correlations. I've used Westphal's and Young approach to resampling to get the p-values for these correlations and apply to them fast discovery correction. As I said, this is my interpretation, or this is the way I'm presenting the graph. This is the meaning of each one of the elements. And if you've got a arrow that goes into the same variable, it means that's the error term. So rather than a covariance, it will be the error term. So imagine you're starting with a story like this. Here's the rotation revolutions per minute. The subject matter expert will say, "Oh, if whether we're in winter or in summer affects the sea temperature. This affects the wind speed, but the wind speed does not affect anything with regards to perceived noise and energy. We start with that. We start measuring. You get the sizes of the effects and the p-values. When you look at the same story, but on the comparison to the correlation matrix that is observed, you say, oh, there's a few cases where this did not work. So you go back to the drawing board with the subject matter expert, and after a few iterations, you come up with a different story, same variables, where whether you are in winter, the sea temperature doesn't affect anything. However, the wind speed does affect other elements. And then you get a better fit. The only difference here, you see here, I still didn't get the error term correctly here, and that is correct because generally I didn't do it linearly when I created the data set. So this is cool. So I'm not saying this process needs to be the only process for generating the model. What I'm saying is this is a good process to interact with a subject matter expert, come up with the variables that are really important to put your time and effort into, not necessarily with one data set, but you can create different data sets to assess the different relationships. Of course, then you have an issue with measuring the correlations. You can work around that. Then once you've done this, this is a very explainable model. If you still want to get to a more precise, predictive, accurate model, then go for it. Use these variables, use the data that you've accumulated with the relationships, with the knowledge about what affects what, and throw away variables that, for instance, based on this, I'm not going to waste my time in doing anything around sea temperature, right? It's wasting space and the degrees of freedom, if you want. Go and apply a more sophisticated and complex modeling approach on these variables. So if you're watching this before the 15th of October 2024, you're definitely, I would like to plug an event that I'm helping organize under the Royal Statistical Society's Business and Industry section around quantum computing. There will be an in-person event in London, in Fenchurch Street, but you can also access it online. Thank you very much for listening.